Wow. All right, guys, as you come in, or if you are here, let me know if you have any questions from the quiz or from homework. Oh my goodness, can you graph a sine equation with a horizontal compression? Sure. Before I get into that, I want to tell you, in the homework, there is one problem that is exceptionally evil. Let me see if I can remember which one it was. I think it was 15. I had a couple people out, yeah, 15 in section 8.1. Just to let you know, 15 and 8.1 is a little bit evil because let me see if you guys are with me on this. If the period is in terms of pi, you want your phase shift in terms of pi also. That makes your scale easier to manage. If your period is a number, you want your phase shift to be just a number. Then they match and it's easier to make a scale. So number 15 in section 8.1, the period's in terms of pi and the phase shift is not in terms of pi. So you just got to go to pure decimals. And there are a few different ways to do that. And I was helping somebody out earlier in office hours, so if you have a specific question about that, but somebody's got a general question about a sine function with a horizontal compression. Do you mean like Schubert? Or Schubert? Yeah. I like when the number is by, oh yeah, you're fine. No, you're probably right. I always forget the terms. So something like this. What kind of number would I have to put next to X?
We can't.
So that it's,
sorry.
Go ahead.
It's out of frame.
Oh yeah, I always forget that. Thank you. I don't mind anybody helping me out. It used to be somewhere where I was never out of frame. It was called a classroom. All right. What kind of number would I put there so it does end up compressing it?
A whole number.
Say again, sir.
A whole number.
Like one?
Not a fraction. No.
Oh, like a number bigger than one.
Yeah.
It can't be a fraction, just bigger than one. So if I put a 4 there, right? Do you want more shit happening to it, or you just want to look at that by itself?
Yeah, like make it super difficult because I'm confused.
Okay. All right. All right, let's do sure. Sure. All right, it's not super difficult, but it's worse. Okay, so the book sort of uses a slightly different terminology and slightly different thing. But you can always go back to what we did together in class and what's on those handouts that I put up on Canvas. The amplitude, of course, is 3 on this problem. Make it 3. What's the period going to be? What's the period going to be for this guy?
Is it pi over 2?
Yes, it'll be the old period divided by the multiplier. So pi over 2. I like it. And what's the phase shift going to be?
To the right, pi over 4.
Yeah, because you take a 4 out. So now it's to the right, pi over 4. I like it. So you can do, and here's something I was talking to somebody about earlier. I really want you guys to notice when I do this begin and end thing, I make the input equal to pi. I'm sorry, equal to 0. So I was thinking about pi. And I make the input equal to 2 pi. because that would mimic, that would tell me where, because normally it starts at 0 and it ends at 2 pi. That is one way to think of a cycle. Right? And I've talked to you before about you could actually consider a cycle to start at negative pi and end at pi. That's fine also, because it's true. Any 2 pi interval in a normal sine will represent a cycle. So pretty decent with that idea by itself. So you don't have to use 0 and 2 pi. You could use anything separated by 2 pi. And you don't only have to do the beginning and the end. So what are these? Let me blow this up a little bit. I'm going to erase this in a minute, but what are these? If I graph what are these points here? This, of course, is 2 pi. This is going to be
Pi over 2.
Pi over 2. I like it. This is going to be pi. This is going to be 3 pi over 2. You could actually set this equal to pi over 2. You could set this equal to pi. You could set this equal to 3 pi over 2 and see what all the points translate to for this shift business. If you needed to, I don't know, for like number 15. I don't know. That's one way to handle it when it's much grosser. There's a mixture of pi and decimal shit happening. Okay, maybe. On this problem, I don't really need to do that because it's not that difficult. So here I'll get, it starts at pi over 4, which makes sense because it was shifted right pi over 4. And if I add pi, divide by 4, it ends at 3 pi over 4, which is good because the period is 2 pi over 4. 2 pi over 4 later is 3 pi over 4. Okay. We stop for a minute. That's another reason why I like to suggest you do all of this as you get used to it, because you can kind of check yourself against what you've done. Okay. Is anybody not okay with what's happened so far? You can always private chat me if you don't want to let it be known publicly for adversion. Jeez, help me. Should run for president. All right, so continuing, I'm not seeing anything from anybody. I've got enough information now to plot this bad boy. Am I going to go? Oh, yeah, let's do this. Let's focus a little more on this side. So there's pi over 4. There's 3 pi over 4. Now watch this. There's one other thing that I used to teach. For some reason, I stopped teaching it, but I might as well bring it back. So you see how the period is pi over 2. Of course, I just deleted it, but how big of a step do I take between? Will it be 1, 2, 3, 4 steps I've got to take to get the whole cycle? Are you guys with me? 0 to pi over 2 to pi to 3 pi over 2 to 2 pi, blah, 4 steps. So if I cut this, man, I'm about to die nasally. All right, if I cut this in fourths, it tells me how big of a step I should take. So that's 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, which is 3 pi over 4. All right, let me stop. Did everybody understand what just happened? Now, you don't have to do this. You could just average these two, and then average these two, and then average these two, and it will do the same thing. Why does that say? It looks like it says square root. Sorry. And now you just plop one there. What's this going to be?
Three.
Yeah. Did I forget anything? No. Okay. So now you just plop, 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 plop. Wow. Yeah. All right. Cool. I like it. Is that all right? That was exciting. So you don't have to do all of this. But you can do all of it, and it kind of like checks itself as
Can
you
you
go.
explain the scaling again? That's kind of what I'm confused on.
Well, this
Like,
step here,
yeah, not just
Okay.
for this equation, but in general, like how to figure out the scale.
all right. Let me see. I need some room. Oh well, go with me right here. So remember what I said earlier. If I do this kind of thing, I'm assuming a cycle to go from 0 to 2 pi, right? And it has 1, 2, 3 stops in the middle. So there's 1, 2, 3, 4 steps I've got to take. So far, so good?
Yeah.
Okay, now, all this shit does is it compresses it, it stretches it, it moves around, all this kind of shit. So it still has 4 steps. It's just this step will tell me how big each step is. So normally I've got to go a full 2 pi. Divided by 4 is steps of pi over 2, which we know is true. Pi over 2, pi, 3 pi over 2, 2 pi. Is that? So
Yeah.
in my normal period, if I cut it in fourths, it tells me how big each 4 steps are. So if I do that with my new period, cut it in fourths, it tells me how big each step is. Because all of these important steps of this thing have to occur the same kind of locations. All I do is I smush it or I stretch it. And who cares about this direction? Doesn't do anything to this. And then I move it around. It still has to be 1, 2, 3, 4 steps that everything happens in. And no part of my sine function gets stretched differently than another part. That's why each step is the same size. The whole thing gets stretched and compressed. This side doesn't just get it and this side doesn't. Doesn't make any sense. Not what the functions we're working with anyway. Oh shit. Is that better or is that not good still? Not good is a valid answer if it's the right answer. Tell me one way or the other. Okay, all right. So you have a lot of options to help you plot these. And you could be incredibly precise with what you identify. And this step is the nice step. I don't know why I stopped including the step size idea, because that does help out a lot. I think I just started just teaching people to get the average and then the average. But I mean, this is kind of nice. Okay, anything else from, is it the same for cosine and tangent? The only difference for tangent is where are your important points for tangent? What are the important points for the base tangent function? The base cycle. Does anyone remember? Where are my vertical asymptotes at? And if you forget, just remember what tangent is. And vertical asymptotes happen where the cosine is 0. So where is the cosine 0?
Is it at pi and negative pi?
No. At pi and negative pi, it's 1 and negative 1. So if you have not done this for yourself, you desperately just need to know the basic trig values for the angles we discussed. 30, 60, 90, 45, 0, right? You've got to know all the trig values for those angles. So, because then, so you figure out a way to memorize those. And I've given you a few ways to do that. Because then if you forget where tangent lives, you break it down to what it is. You say, okay, where's cosine 0 at negative pi over 2 and pi over 2? Right, at pi over 2, its cosine doesn't like it because it's all y. There's no x piece to that. Oh shit, cosine hates it. And then negative pi over 2, same idea. I can't do that on camera. Right. It's all y, it's no x. So cosine is like, I don't like it, it's 0. How do I get the amplitude? Oh, it's just the number that's multiplying outside. That's all. So whatever sine's outputs are, this just triples it. That's why that's the amplitude. That's one of the most straightforward things about trig function. It just stretches it. If it was a fraction less than 1, it would compress it. Is that all right? All right, so I got 2 quick questions in a row here. Hold on. So I got number 21 on section 8.2. Let me see. All right. Sorry, driving myself crazy with if it's allergies or what the hell it is. I don't know. So A2 number 21. Ooh, yeah, that looks yummy. All right, let me show you this. So there's the problem. Jeff, why do you do that? That doesn't help anybody. Okay. Nah, go away. Stop. Okay. All right. You can see, there's the problem. Number 21. So let me write it up here on the board. Don't worry, I will stop sharing in a second. Well, let me use the same thing they did. M of X, sure, book. All right, so there's a couple of interesting things about this problem. First off, it's cosecant, which means you're really graphing what first? 35 inches. I have no idea what that. Oh, I see. Neat. All right. I'm sorry. So many, yeah, the problem we just had was 3 sine, and with my horrible writing, it looked like 35 inches. Sorry, all right. Sorry. That's bad. What function do I graph first that I can then plot this kind of on top of?
Sine.
Sine. I love it because cosecant is 1 over sine. I like it. So I just kind of pretend like there's a sine here for it at first. So now I just do all the same steps as before. What's my amplitude going to be? Six. I like it. And that's for sine. There's no real amplitude for cosecant, but for sine, there's an amplitude. And then I can plot the cosecant on top and bottom, right? What's my period going to be? What's the multiplier? So 2 pi divided by what?
Pi over 3.
Pi over 3. I like it. So the pi's cancel. Divided by 3 is times 3, so I get 6. Is that cool? Divided by 3 is times 3. Just like minus 3 is plus 3, right? All right. And then I've got the phase shift. So if now watch this. This is where things get a little interesting. You got to take a pi over 3 out. You just have to. So pi over 3 divided by pi over 3 is 1. What's pi divided by pi over 3?
1/3.
No. And this is such a misunderstood dude. Isn't this just pi times the reciprocal? Isn't that all that is? People just make such a big deal out of that, but it's, if you're dividing something by a fraction, you multiply by that fraction's reciprocal. No big deal. Pi's cancel, I get 3. Because when you distribute this, don't you want the 3's to cancel? There's no freaking 3 here. So of course it's got to be 3. So that when you multiply this, you just get pi left. You can kind of double check yourself. Check yourself. Ooh, I'm getting a little Laggy. Okay. All right, let me stop for a minute. How's everything so far? Let me know the minute I lose you. Amplitude is the multiplier on the outside. Period is the 2 pi divided by this. Why is it 2 pi? Because it's based on sine. If it was based on tangent, this would have been pi because that's the period of tangent. So all these little things I keep saying, the period of tangent is pi. Memorize that. You got to know it, right? Cosecant is 1 over sine. Memorize that. You got to know it. So now I know the phase shift. What's the phase shift going to be?
Left 3.
Left 3. I love it. Got it. All right, and I'm not going to do this whole problem for you because I think this is a homework problem, but you could do your begin and end. I don't know if this helps out. Did I already answer the question behind this? Let me see. Number 21 and 8-2. That was this one, right? Is that better out there? Person who asked about this problem?
Yeah, you answered the question. I did the whole x plus 3 times pi over 3 wrong.
Oh, shit. Okay. All right. And I want you to realize, I'm sorry, go ahead.
I was just saying thank you.
Oh, okay.
Cleared that up for me.
This whole step here, I don't really need. I know it's left 3, and then I know the period is 6, so it should end at 3, right? But the weird thing is, where are my little steps going to be between those? Is everybody cool with that? Period 6, it's left 3. So I know it starts at -3 and it ends at 3. But now I've got to figure out where are my actual points that the maximum and the intercepts and the minimum happen, right? Maybe? No? Maybe? No? You suck, Jeff. So for that, you could do the thing I showed you. You take the period, divide it in 4 parts. So now I know I have to take a step of 3 halves. Is that all right? And of course, this is if I cut it in half and then cut it in half and half, it matches with the step of 3 halves. I don't know if you followed me on that. So either way, it gets you. So there's a multiple ways to get to the same conclusion, but if you do sort of all of them or a few of them, they should match with each other. They should check with each other. And of course, the ultimate check is just to plot the damn thing in a graphing app or calculator or whatever. Check, not way to do the work. That's a check. Check, check. Okay. Anything else, guys? Oh, let me see. I missed a few. 15 from 8-1. Oh, yeah, that's the one. There we go. That's the one, I think. Might as well talk about this with everybody. I talked about this with somebody in office hours. Number 15 on 8-1. Let me share that with you, and I'll copy it down. This is the evil number 15. I almost feel like it was a typo, but I don't know. Knowing this book, maybe not. Don't worry, I'll turn that off in a minute. Okay, so you guys all see that problem. Where's my, oh, there we go. Get out of here. So you just start attacking it. You don't even know necessarily yet, but what triggered me when I saw this problem, the period is going to have a pi left in it because there's no pi here to cancel, but then the shift is going to not depend on pi. So that kind of sucks when that happens. It's just too bad. Just, so sad. Too bad. So amplitude is easy. Bam, ba, bam, bam. What's my period going to be? 2 pi over what?
8. So pi.
8. Pi over 4. Kick ass. What's my phase shift going to be?
Left 4.
Left 4. I like it. And let me see. How do I want to say this? So there's no real good way. There's a few ways you could do this. But you could just take everything to decimal because that is not going to play well with that. Does that make sense? So one way you can do this is my step size. Holy crap, that's like a triple decker Z. My step size, if I cut this in fourths, it tells me how big my steps are going to be. They're going to be pi over 16. So you could, I know it's left 4, and then I go pi over 16, pi over 16, pi over 16, pi over 16. And to kind of check yourself, you can do the begin and the end. Right? 8 times x plus 4 equals 0. 8 times x plus 4 equals 2 pi. I really want that to make sense. If I make the input and the output where sine normally begins and ends, when I solve for x, it tells me where this thing begins and ends. Now, at least one cycle of it, right? So x equals -4 here, which matches up with this guy. And this one, if I divide by 8, and then I subtract 4, I'm going to write it this way on purpose. Why does that make sense for an ending? Because it starts at -4 and it ends pi over 4 later. So of course it's going to be -4 plus pi over 4. So you actually could do that. It's a little unsatisfactory in a way. All right, is that enough to get going on that number 15? I mean, that I've done a lot of shit for you. I'm going to stop there.
For like those problems, they're asking where the max and min are. Do they
Yes.
want us to tell them after we graph it, or is there like an equation we have to use?
So the easiest way to do it in this problem is to do it after you graph it. But to be honest, you know for sine, if you use 0 and 2 pi, you know that the max occurs at the first step. Are you guys with me? The max occurs one step in, and the min occurs 3 steps in. So if you know your step size, you could do this work, not graph shit, and just go, okay, one step away from -4. So if I add pi over 16 to that, that's going to be where the maximum is. And the min is going to be -4 plus 3 of these. 3 steps in is where the min's going to be. But it's kind of easier to graph it because you do that to graph it, and then you can just see where the shit things happen. So it's just easier if you have to graph it anyway. Just answer the question after you graph it. Does that make sense?
Yeah, thank you.
I like it. I need you to understand also, everybody, that this is very, very technical. All this graphing we're doing is very technical. There are multiple ways to achieve the same things I'm achieving this way. This is just the way I kind of like to show it. This isn't necessarily even the way I would do it. But I think it's the best way to sort of start learning. But you can improve on this for yourself, for sure. Let me see. Did I miss anything? Oh, sorry for going back to number 21 for A2. But how do you graph? Wait a minute. There's no inverse sign there, is there? Wait a minute. A2 number 21. Let me see. Wait a minute. Oh, so it's not in, be careful, be really careful, be really careful. It's not, okay, so let me take this away. Has everybody got what they want from this business? More than you ever wanted? I'm sorry. Okay, here we go. Somebody's asking me about cosecant. So if I graph a sine and I get something like this, right? Is that cool? Let's say that's my sine, right? How do I graph cosecant there?
Well, where are my asymptotes going to be? So let's say this is my sine. It's been shifted, right? It's my shifted sine. And now I want to graph cosecant. So this really should be dotted, right? Ooh, that was neat. Because it's not really the answer yet. All right. How do I graph cosecant? Well, where would the, and remember, cosecant is 1 over sine. So where are the vertical asymptotes going to be? Where this does what?
Are they at 0, pi,
Yeah,
2
the
pi?
x-intercepts. So there's going to be a vertical asymptote here, because 1 over that is going to be infinity. All right, there's a vertical asymptote there, vertical asymptote there. And then I throw in my wee-ha, wee-ha, woohoo, wee-ha. All right, pretend like that's 1 point. Is that all right? I mean, that's how cosecant and secant works. You graph the associated sine or cosine. Vertical asymptotes happen where whatever this function is 0 because it's on the bottom. So of course there's going to be a vertical asymptote there, right? Let that make complete sense. If the bottom is 0, the function with that bottom 0 has a vertical asymptote there. Like, which explains why tangent has vertical asymptotes, because tangent is sine over cosine. So cosine, where cosine is 0 is where tangent has props. Is that enough for, what's interesting then, tell me how many humps are there for a cycle of a sine? Is that a weird question? There's 2. Is everybody cool? There's 1, 2 humps. So how many humps will there be for cosecant? 1, 2. I mean, it's, yeah, so I know what you mean, but this is one function. This is a cycle of this function. It's going to, of course, keep going forever after this, right? Forever and ever and ever and ever and ever, both directions. Okay, I like it. Yes, that's right. 2. Yeah, it looked really evil there. Sorry. All right. Let's see. Makes a lot of sense. Thank you. Okay, good. That's my favorite phrase. Currently, the quiz, this is good. Let's talk about the quiz for a minute. I currently have the quiz slated for this Thursday. We really only have one section left to talk about, but I understand that you might want to take a little more time. So is it okay if we switch the quiz to be on Monday? Tell me how you really feel. You guys can't see the private chat, but somebody just screamed yes. Okay. So we can make the chapter 8 quiz on Monday. If somebody will email me, I can change the due dates for the homework on chapter 8. So you guys don't freak out. Please, dear God, if you miss a due date, just turn it in when you can. It's that simple. I only let that hurt you if you turn a lot in late or if it's very late. But what all of you should do to get ready for quizzes is do as much of the homework as you can to get ready for the quiz. It's that simple. So if it's almost time for the quiz and you haven't even started this section, maybe do every 8th one or something. Do some of every kind of problem because you are looking out for yourself. You're like, that's nice, Jeff. You want your homework turned in. That's nice. I'm going to do what I need to do to get ready for the quiz. And I'm like, all right, whatever. Does that make any sense? I've got rules. Yay, I've got rules. Who gives a shit? My rules are there to try to force you to do what's right. If you can do what's right yourself, then screw my rules, right? I'm still going to come down. I'm just going to go, well, shit's your homework, but this is generally true for all of college. This is generally true for all of life, to be honest. Just be careful about some rules. All right, that's enough. Okay, so that's officially Monday. And hopefully somebody's emailing me about the homework. I can shift that. Anything else about 8.1 or 8.2? I want to get into 8.3 because I'm crazy. Any other examples somebody needs or specific questions about anything? Okay, I don't see anything. All right, so we're going to get into 8.3. And what I want to ask you first thing is, let's look at the sine function first. Let's see, how specific do I want to be? Sort of specific, okay. Yeah. Okay, that's fine. So we've got bam, bam. And then this is going to go there, there. So we've already discussed this problem. And real quick question. If I picked the coordinate system up, do you see how I just have to move it over 90 degrees and then it's cosine? Right? I mean, that we talked about that already, but the way of drawing this, you can see the octopus here. That's the cosine octopus. The main problem with this function, if I want to start talking about the inverse function, I want to talk about this, which does not equal 1 over sine. I don't even feel right writing that, even though it's a not equal to. Not equal to this shit. No, get out, stop it. No, stop. Sorry, did I make a point of that? It's just a really unfortunate decision as to how to, but again, we know by now that this means inverse function. What's this function? Anything. So it could be sine. Now, let me tell you this. There is another way to say this that I personally don't like, to be honest, but you can use it if you want to. It's called arc sine. That's another thing. It means the inverse of the sine. So somebody tell me, before we even talk about what needs to happen to allow this to exist, can somebody tell me, like, if I have y equals sine x, what physically is x? That's a weird question. I don't care. Or geometrically, what's x? Oh, I'm sorry. You can go. Whoever. I think that person already left. All right. I keep missing things in chat. Anybody? Geometrically, what's x?
The angle.
Yeah, good. So x is an angle, and y is some number that represents the ratios of the sides of the triangle, blah, blah, blah. Is everybody with me? So what is the output to inverse sine going to be? What is the output going to be for the inverse sine?
An angle.
An angle. I love it. All right. So we kind of already know, let me see how, if you know this, what should the inverse sine of 1/2 be? What do you think in your head? You think, what angle do I take the sine of to get 1/2? We have to think backwards about it because it's an inverse function. Does anyone know what that would be?
60.
Oh, I got 2 people at once, I think. Say it again.
60.
60. 30. Okay, I got 2 options. Sine likes y, so it's going to be the smaller option when it's further from the y-axis, which means closer to the x-axis, so it must be 30, otherwise known as pi over 6. Now, to be honest, I wanted to hear there's an infinite number of answers, but not technically no. So that's the part we got to talk about now. This is officially what the inverse sine of 1/2 is. Even though if I just asked you, what do I take the sine of to get 1/2? You can give me an infinite number of answers. Could you not? Maybe you couldn't. I don't know. Can somebody give me another angle? So if my question was the sine of what is 1/2? One answer is pi over 6. What's another answer?
13 pi over 6.
Yeah, why do you say that?
Because, I mean, technically it's the same angle, just another revolution.
Cheek ass. And so you can keep going in both directions forever. You can even do negative pi over 6, right? As long as it's where, not negative pi over 6, God. You could, my point I was just about to make told me, oh yeah, Jeff, that's not right. As long as it's where the y is positive, so it could be any reference angle there and any reference angle there, that comes out to be 30 degrees or pi over 6. So of course 5 pi over 6 would work, because that would be a positive sign. Let me stop for a minute. Does everybody understand that? But what do we call the function that you can invert? What's the name of a function that is invertible?
One-to-one function.
1-to-1, which means all this extraneous possible answers, the infinite number of possibilities, can't be allowed to happen. It's supposed to be 1-to-1. And of course, graphically, we see the problem. There's an infinite number of things. You can see it, in fact, if I do this. There's an infinite number of possibilities that equals 1/2, and you can see that all the places where it matches with 1/2. Right? There's pi over 6, there's 5 pi over 6, 13 pi over 6 is over there. So of course, we've already talked about this, but who remembers, how do I take care of this problem? How do I make this something invertible? I have to do what?
Limit the domain.
Yes. And there are other ways to do this, but the way we've decided to do this is to limit it from here to there. Negative pi over 2 to pi over 2. Do you see how that hits all the values that sine takes on? It's not a complete cycle, but that's not, we don't want a complete cycle, because then it's not invertible. So we focus on this to this. All right, so it goes from -1 to 1, and it does this funky little woo-hoo. We've never really seen a function, even though it's a part of the sine function, just graphing this looks weird as shit, right? Just this one piece by itself, but it's totally invertible now. So what is the range of inverse sine? What's the domain of sine? What's the domain of the sine, the domain that we had to cut it to make it work? What's the domain?
Negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. So what's the range of inverse sine?
-1-to-1.
No, come on. If the
Negative
domain,
pi over 2 to.
yes, because all the x's switch with all the y's. The range of this one, of course, is -1 to 1. So the domain of this one is -1 to 1. How do inverse functions work? All the x and y shit switch, which means on a grand scale, the domain and range switch. Oops. All right, let me stop for a minute. Some of you guys might realize that this leads to a possible problem. So the answer we get when we do an inverse sine in like a calculator or something is a reference angle type thing. So watch this. Let's try this in our calculator. I'm going to put a problem up here. Where, Jeff? I don't know. So say I want to do the inverse sine of, you can do it, Jeff. Let's just make it 1/2. But I know that my answer is in the third quadrant. Right, so they tell me it's in quadrant 3. So if we do that in the calculator, it didn't matter what I picked it. No, not really, but oh well. Rawr. Let me see, let me stop. Where? All right.
Sorry, gotta wake my calculator up. This is gonna take a minute. Poor little dude. You need me tonight? Yeah, come on. There you are. Oh, neat. That is funny. Why do I have it? Oh, because we did this last time. Look at this shit. Hold on. Where you guys go? I've lost you. My whole class is gone. Hold on. There you are. All right. Oh, this is so exciting. Old man using technology. We did this last time. This is exactly the problem. This is really freaking me out. So if I know the answer is supposed to be in quadrant 3, this can't be my answer. That's in quadrant 1. So what I get is a reference angle. Is everybody cool with that? So what's the actual answer then to that problem I put up there?
150.
Beautiful. 150, of course. If it's a reference angle of 30 degrees, then that's going to be 180 minus 30, 150. That's in the second quadrant. Did I say it's third quadrant? My God, Jeff. Don't, that past Jeff guy, you got to keep an eye on. Oh, jeez. All right. So let me give you a little bit more freaky of an example. What if I knew it was in, let's do a quadrant 3 for real this time. I knew it was in quadrant 3. And I want to know the inverse sine of negative point. Let's do this. Yeah. This is gross. I love it. Why am I so excited about that? I don't know. And real quick, what's the biggest number I can put in here? What's the smallest number I can put in here? I just basically erased it, but and since it's inverse sine, its domain is equal to the range of sine. So what's the smallest number is what's the smallest domain piece of sine?
Negative pi over 2.
No.
The smallest.
What am I trying to say? Oh, I just said it backwards. I'm sorry. Let me try this again. So this guy's domain is equal to the range of sine. So what's the range of sine? Negative 1 to 1. So what's the smallest number I can put in here? Negative 1. What's the biggest number I can put in here? 1. Right. So we're going to look at what the calculator does if I break that rule. We'll do that next. But if I put in here inverse sine of negative 0.29, I get this. Now that is degrees. I think there's a few people, you got to be really careful. I didn't make a big enough point out of this. I thought I told you the story about, did I tell you the story about how I got an entire quiz wrong because I was in the wrong mode? And the teacher, normally you can catch that because you'll get stuff like the tree is negative 450 feet. And you're like, oh, I must be in the wrong mode. But the teacher had purposefully picked examples that it would come out to be reasonable. What an asshole. So young Jeff learned this lesson easy. You got to be careful about the problem. If you have radians, make it radians. If you have degrees, make it degrees. What's interesting about inverse sine is if I'm in degrees, the answer comes out in degrees. If I'm in radians, and I do the same problem, the answer comes out in radians. Oh, that's neat. I cannot take credit for. The inverse sine of negative 0.29 almost is the same thing in radian. I'm sorry, I can't take credit for that. That is freakadelic. That's going to trip me up. Does everybody understand why I'm freaking out a little bit? Okay. But let's stick with degrees. Let's stick with degrees for right now. Get down there. Get over there. All right. So again, just to bring it back. So we got this. That is not in the third quadrant, right? So obviously, what's the actual angle then? So notice something about inverse sine. Let me stop doing this. Inverse sine, the output is going to be between negative pi over 2 and pi over 2. So the output will always be quadrant 4 and quadrant 1. That's what the output will be. You need to adjust it in certain problems to match up with what
what quadrant you're supposed to be in. So we just got negative 16 point whatever the shit. So actually it should be here. So the weird thing is you end up adding 180 to 16 point whatever, right? So you get 196.8579. Good Lord. All right. And let's double check that. Is everybody cool with what's happening so far? When you, because of the restriction we had to put on the domain, that means that my output for inverse trig will be restricted also the same way. So if I need to be in a quadrant that my range doesn't cover for that, it's a reference angle. I have to adjust it. So if I want to check this real quick, if I do sine of, what did I just get? 196.8579. You can do it, Jeff. 8579. That's almost. There's the negative 0.29. I just rounded it, of course. Is everybody cool with that? Okay, okay. The few people I can see are cool with that. All right. So now let's look at cosine. Same thing's going to happen to cosine, except cosine is actually nicer than sine. And let's see why that's true. Oh, let me see. Am I? No, I don't know where I am. Let's see. Bring you guys back over there. There we go. So to do this a little bit quickly, cosine, of course, goes like, so this will be pi over 2. This will be pi. Does my scale look all right? Yeah, sort of. 3 pi over 2, and then negative pi over 2. I don't know why I'm using all this shit because I'm going to show you. I guess I should do this just to show you what happens. Bam, bam. So there's the octopus. Get in there. Okay. So you can see the problem. And this is a nicer thing we can do. What we basically do is we chop it here to there. And that's a really nice thing because now all of my outputs will be between 0 and pi. They'll be in quadrant 1 and quadrant 2. I'm not going to get any negative outputs, so they will be purely reference angle answers. And later, when we start doing inverse stuff for triangles, inverse cosine kicks ass because the angles in a triangle can't be more than 180. So they're always the exact right answer then. No reference thing to them. So later we're going to learn something called law of sines and law of cosines. And one of the two of those will always be more definitive. The other one is going to be a little bit more vague. Too bad. All right. So everybody cool with what I just said. So the actual graph of the invertible function looks like this. And just trying to graph this freehand without, so it's got this nifty little, looks like a, what do you call it? Graffiti kind of thing. Anyway, is that cool? So the output for inverse cosine, the range will be 0 to pi. Because the domain of cosine, the domain we have to restrict it to is 0 to pi. And the range here is -1 to 1. So the domain here is -1 to 1. Can we stop from, oh, shit. Let me straighten my house. Okay. There we go. I don't know how to make that better. Too bad. Okay, so then you can do similar kind of problems. You're not going to have to, thankfully, the top of my head, I really don't think they're going to make you graph like shifts of this thing. That would be kind of insane. So let's take a look at what they're going to make you do with this stuff. Oh, before I forget, that's right. Tangent. Let's talk about tangent real quick. You leave that there for a minute. Tangent's kind of nice because its base cycle goes from negative pi over 2 to pi over 2. Looks like a cubish dude. So it's inverse. So this, if I just restrict it to negative pi over 2 to pi over 2, oops, these can't be inclusive because they're vertical asymptotes. And the range is, of course, negative infinity to infinity. All right, let me stop for a minute. Is that cool? I got to restrict it to be this because it does repeat forever, but I got to throw that shit out. Now get out. I got to focus on this. So then it's invertible. It's 1 to 1. So the domain is negative pi over 2 to pi over 2. The range is negative infinity to infinity. So when I do the inverse tangent, do that in red, right? So if I have the inverse tangent, its range will be negative pi over 2 to pi over 2. And its domain will be negative infinity to infinity. And this guy's graph, I don't really focus too much on the other guy's graphs, but this guy's graph is really kind of nifty. It looks like this. Whoa. It's got horizontal asymptotes now. Kind of makes sense when you invert something with vertical, they become horizontal asymptotes. Is that cool? All right. It's just kind of nifty. The other ones are kind of boring. That's not the most exciting thing in the world, but too bad for me. So when you do an inverse tangent, your output is going to be a lot like we have with inverse sine, right? It's going to be between negative pi over 2 and pi over 2. So it's going to be another reference angle situation. You got to be careful about what quadrant you really want to be in. Okay, I like it. Oh, let's do this before I go in the book. I'm going to kill all this. What time we got? Okay, I'm going to stop here in a minute. I want to do one last thing, I think, with this for today. Nobody's yelling at me. Good. Some of the coolest shit. All right, let me focus on one piece of this. So if I write down here, inverse tangent of 3/7. What is that? Again, physically, that represents a what? The answer to that would be what? What kind of thing? Physically, geometrically.
An angle.
An angle. Now go with me. Now watch. Go. How would I kill this? What would I do to both sides to kill this? By definition. You could do it. Please, dear God, nobody say divide by the, oh my God, that would drive me insane.
Take the tangent of both sides?
Yeah. By definition, how do you kill a function with its inverse? You apply the inverse. These kill each other. So if I see inverse tangent of something, some ratio, whatever the hell, that really means the triangle where the angle and the base makes tangent 3/7. So this sets up by itself. You can always write this just to really make sure you know what's going on. But this means the angle whose tangent is 3/7. So what's 3? The x, the y, or the hypotenuse is 3.
Y.
Good. And of course, 7 would be the x, right? Now, no. I love you guys. I promise, this is the last problem. What if the problem was this? The actual problem said, please find the sine of the inverse tangent of 3/7. You guys with me? Why does this make sense? What should always be inside of a sine? An angle. Isn't that what this is? That is an angle. That's the angle that does this shit. Can I find the sine of it now that I drew the triangle that this creates? How do I find a sine? What's the last side I need? This side, right? It'll be 9 plus 49 square root of 58. So this would equal 3 over rad 58, which is 3 rad 58 over 58. So if you see a problem like this, you focus on this guy. This guy represents a triangle. The angle in the base sets up this ratio of the sides. Okay, and then you pick the right sides for whatever this trig is. Then you can answer whatever shit they got out there. Now, next time we'll talk about what if the inverse is on the outside? What does that do? And we'll talk about that next time. I think that's plenty for today. Woo! So we're not quite done with section A3 yet. Let me know if you need to hang out, if you got any other questions. Otherwise, we're done. Let me put my head somewhere decent. All right, here we go.
Thank you.
Anybody have questions? No. I'm headed out. I'll see you guys. Bye, everybody who's still there.